So in this lecture, we're going to see about how reflection, transmission, and refraction happens of light. We are talking about light in terms of electric and magnetic field, right? So electromagnetic wave. So how at an interface. So this is the interface, and it being incident at an angle. So here you can see Ki. The K is the propagation vector. I denotes the angle of I denotes the incident propagation vector. Okay, so here I denotes incident propagation and R denotes the reflected propagation vector and T denotes the transmitted propagation vector. Now it is incident at angle theta I and it is reflected, some part is reflected, some part is transmitted. Now we are going to find out the amplitude of each part that is reflected and transmitted, and we'll see how we can actually derive the laws of reflection and refraction using these set of equations that we've derived for us as our in electromagnetic theory. So we'll start out by writing the incident electric field. So we have the incident electric field. You can see that this is the incident electric field, and incident electric field has some amplitude and it has some phase factor. We only take the real part in the solution, but this is the solution to the Maxwell's equations, that the wave equations that we derived. So this is the solution that we use, and the magnetic field is just the cross product of the electric field with the propagation vector, and it is divided by the velocity. Here it is the velocity in the medium 1. So this is medium 1 and this is medium 2. Okay, this side is medium 1, this side is medium 2. Let me write it. Okay, so yeah, I think it's mentioned here. So this is medium 1 and this is medium 2, and the reflected ray will again have some amplitude and some phase factor, and its magnetic field component again is given by the same formula, and the transmitted part, now you can see that the only difference here is the velocity is different here, right? Obviously here the amplitudes denote the transmitted amplitudes and the phase factor is different, sorry, the velocity is different. So here you have the velocity v2. Now the frequency is fixed at the start when this light, if you shine some, if you are, if the incident in the incident light you shine some laser or something, the frequency is fixed at that instant, right, by the incident light, and during reflection and refraction the frequency doesn't change, so the frequency is the same. So the frequency and uh, the wave number and or the propagation vector and the here we have the velocity are related this way. Okay, the angular frequency, you can see how that relation goes. I'll write it down. So omega is equal to 2 pi nu, right? Nu. Now you can write this equivalently as k is equal to what? K is equal to 2 pi by lambda, right? K is equal to 2 pi by lambda. So if you write it as k into v, okay, v, okay, k into v, okay, what you'd get, v is nothing but, or the velocity nothing but nu by lambda. So you can write omega as, this omega can be written out as propagation vector times the velocity, okay, times the velocity. So if it's a scalar, k, it's a scalar, it's called a wave number. If we're talking about a vector, then called it a propagation vector. And it's this is how they are all related. And if you see ki, you can equivalently rewrite this equation, and on rewriting this equation we can say that ki is equal to kr is equal to the how it's related to the transmitted uh, propagation vector is by v v2 by v1. Okay, so we're just rewriting this equation here. Now at the interface, okay, at this interface where z is equal to 0, okay, at this interface, at this point z is equal to 0, at this point all the phases, okay, are the same. Okay, all the phases are must be the same, the phases must be the same, only their amplitudes will be different. So that's why we're leaving the amplitudes in brackets. We'll figure out the amplitudes later on. Now we'll talk about these phase factors. Now already this time factor is equal, omega t, everywhere it is omega t. Okay, everywhere it is omega t. So these propagation vectors now ki dot r should be equal to kr dot r is equal to kt dot r at z is equal to 0. Okay, and if to write it out explicitly, now r is the position vector, right? So when you dot kl with r, it will pick out the x component with x and the y component of ki with y, and similarly you will get this entire expression. Okay, so but now let's equate the components. Okay, we'll just equating the components here. So if these have to be equal, they have to be separately equal. Okay, that is their y components have to be separately equal, their x components have to be separately equal. Okay, and we can, supposing we confine our reflection, the process, this what is happening to the xz plane. Okay, we are talking about the xz plane. In the xz plane, y will be 0, right? In an xz plane, y will be 0, right? Y is 0 in an xz plane. So when you substitute that, so when you substitute y is equal to 0, you get these set of equations, right? And from this what we can say is, okay, we can say that the first law of reflection can be proved, that all the incident, transmitted and reflected vectors form a plane called the plane of incidence, right, which includes the normal to the surface as well. And now from equation 9.97, okay, which is this equation here, we can say that there we're talking about the, so equation 9.97 says that the x component are all equal. So if the x components are all equal, so these are the x components written out explicitly. So you can see in the figure, so this will be the, so this will be sine ki cos theta component. Okay, this will be cos theta component, and along the vertical, the x component that we've taken axis, it will be the ki sine theta component, right? We've taken the vertical axis to be x, so this will be ki sine theta component. Okay, so we just write out the vertical components are, so we just write them out explicitly, and we can say, okay, in view of equation 9.92, which is, so according to this equation, ki is equal to kr, right? So ki is equal to kr. So from, because of that we can say, so we can say when ki is equal to kr, both will cancel out, and we can say sine theta is equal to sine theta r, or theta I is equal to theta r. So this is the angle of this is the second law of reflection, which says that the angle of incidence is equal to the angle of reflection. And how the angle of incidence is related to the angle of transmittance or refraction, we can say talk about, okay, from this equation. So ki, you can see ki is related to kt this way. Okay, ki is related to kt in this way. So now we just make that substitution here, ki and kt, you just make that substitution here, okay, and you will get the Snell's law. Okay, you will get the Snell's law. So this is the Snell's law, the law of refraction, right? The law of refraction. So N1 is the refractive index. Okay, so N1 is the refractive index. So refractive index is just the ratio of velocity. So it is the ratio of the speed of light in vacuum to the speed of light in the medium. So this is, so that is how we get it. Now let's solve for, we've so far derived all the laws of reflection and refraction. Now we have to get these amplitudes, right? So we have to get these amplitudes that we left out, okay. So let's try to get them. Okay, what we do is we apply the boundary conditions. You remember we got the boundary conditions for electromagnetic waves using Gaussian pillbox and Amperian loop. We applied Maxwell's equations and obtained the boundary conditions. So these boundary conditions, when applied here in this case, where this is, so here you can see that the perpendicular, so here there is no free charge or current. Okay, so there is no discontinuity in the components. So here when we apply these boundary conditions to our case now, so we get these set of equations. So I'll just show an example. So E1 is nothing but all the fields in the electric field in the medium 1, which is perpendicular to the interface. Okay, which is perpendicular to the interface. So that will be EI and ER. Okay, that will be EI and ER. Okay, so along the z direction, so that is denoted here, that is the z direction, the perpendicular direction. And on the medium 2 we have E2, on the other side we have the transmitted amplitude, and that also should be in the z direction. Okay, the perpendicular direction, that is denoted here. And similarly we apply all the other boundary conditions and we get these set of equations. And the magnetic field is related to the electric field. So supposing we saw this earlier, if you know EI, you can find out BI using this formula. Okay, so this is just the cross product of with the electric field, cross product with the propagation vector divided by its velocity. Now, as I said, we are already taking the direction of polarization to be along the xy plane. So we are taking the xy plane. These vectors are lie on the xy plane. Okay, that is the electric field vector. The electric field vector lies in the xy plane. So we just put directions now. So we take the incoming direction to be negative. Okay, so the outgoing, the reflected direction will be opposite to the incoming direction. So it is positive. And the incoming direction, the incident direction, and the transmitted direction will be the same, so it is negative. And so the first equation becomes this expression here, as I'm pointing out, and the second equation becomes 0 because 0 is equal to 0 because the electric field is in the z direction. So the magnetic field will be in a perpendicular direction. So along the same direction, the magnetic field will be 0. Okay, and then we have And then in the xy plane we have only the cos component of these vectors. And from equation 4 we have the magnetic field, which is we use this formula here to write it out in terms of the electric field itself. Okay, we write it out in terms of the electric field itself. Okay, so now what we're going to do is we're just going to use our laws of reflection and refraction that we derived. So the laws of reflection that we derived were, we said theta I is so in all these equations we're just going to substitute theta I is equal to theta r. Okay, theta I is equal to theta r, and this is the second law, and the Snell's law also, which is, I just pointed out here, Snell's law also we use. Okay, Snell's law, this Snell's law also we use. So this equation and this equation we make use of now, and when we substitute those equations, our equations reduce to these set of equations now. Okay, these set of equations where beta is nothing but this quantity. Okay, here this is permeability multiplied by the velocity. Okay, but here we don't write it in terms of velocity, we write it in terms of refractive index. Okay, in terms of refractive index, and this alpha is nothing but the cos, this ratio here, the ratio of cos of t by cos of I. Okay, so when we substitute all these equations we get the Fresnel's equations. Okay, the Fresnel's equations relate the amplitude of the reflected wave in term, right? You can write the amplitude of the reflected ray, electric field component amplitude, from the by knowing the incident amplitude and these quantities alpha and beta. Alpha and beta are nothing but these set of quantities, right? Alpha is the, so you, the refractive index you have to know for the two media, and you have to know the t angle of incidence and the angle of transmittance, and there is the angle of refraction. So if you know these two angles, you can write out the resultant amplitudes, that is the angle of transmittance and angle of reflected reflected, the angle of the electric field that is transmitted and the electric field that is reflected, the amplitude of the electric field that is transmitted and reflected from the incident amplitude. Okay, from the incident amplitude. These are known as Fresnel's equation.